Thank you, Joy, and welcome everyone to today's Synergist webinar, Flow Calibration Essentials for the OEHS Professional. I'm Kay Bechtold, Managing Editor of the Synergist, the magazine of AIHA. I'd like to thank everyone for joining us today, and especially Mesa Labs for sponsoring this webinar. Today, we're excited to welcome speakers Ram Parameshwar and Lawrence Durio. And now I'll turn the presentation over to Ram to kick things off.
Thank you, Kay. Good morning and good afternoon to everyone who's joined us today. I'm very excited for this webinar. I am Ram Parameshwar, Staff Product Manager at Mesa Labs for our instruments portfolio of products, where I lead upstream development and downstream commercial initiatives. My background is in instrumentation and diagnostics, spanning applications in general industrial, power generation to medical devices and life sciences. Once again, very excited to join you for this all-important webinar with my co-presenter, Lawrence, who I will turn it over to introduce himself.
Good afternoon, good morning, good evening, according to your time zone. I'm Lawrence Durio. I'm a longtime industrial hygienist. Have a master's degree in industrial hygiene, regulatory, chemical manufacturing, and consulting background. Currently, at my age, mostly do industrial hygiene and environmental expert witness work. Also teach EPA, DEQ, HUD certification courses. Through my career, I've been more a field industrial hygienist, applications and getting the job done, not so much an academic, though I have taught at university and medical school levels.
Great, thank you for that, Lawrence. Today's webinar will be focused on defensible exposure data and maintaining sampling integrity. This is crucial for industrial hygiene and OEHS professionals, as small and controllable errors could lead to costly invalidations. We will first dive into what is calibration and why it's essential to ensure integrity, a foundational but sometimes overlooked process that may have consequences if not done correctly. We'll then move into a small history over the evolution of flow calibration and then leading us into how primary standards came to be and how they play an integral role. The second half will include application specifics, common pitfalls, a few insightful cases, best practices for maintenance, and finally, we'll wrap up with Q&A. A little bit about Mesa Labs. Mesa Labs is based out of Lakewood, Colorado. We are a manufacturer of critical quality control tools for regulated settings involving general industrial, healthcare, life sciences, and research. We operate with a focused mission of protecting the vulnerable. We do this across 4 core divisions. Calibration Solutions, the division that I represent today, enables the accurate measurement and calibration of critical environmental parameters within regulated environments where traceability and data integrity are essential. The other 3 divisions across Mesa deliver solutions spanning sterilization and disinfection control, automated systems that support drug development and protein analysis, and genomic testing solutions for clinical laboratories. Despite being highly diversified, our company thread is measurement integrity. Within Calibration Solutions, we operate 6 distinct product lines, each serving specific measurement applications. The product line that is dedicated to gas flow calibration is DryCal, supporting critical applications across industrial hygiene, OEHS environments, as well as broader industrial sectors, including semiconductor, automotive, and pharmaceutical manufacturing. The other 5 product lines span ambient air sampling, medical monitoring, and data solutions for life science applications, and bottle cap torque testing units. With that, I will turn it over to Lawrence to walk us through what is calibration and why it matters.
Okay, first, what is calibration? It is comparison of an instrument to a known standard, the emphasis being known. Normally for industrial hygiene purposes, at least within the context of this webinar, we're talking about airflow, though the general principles apply to acoustics and radiation, other physical agents. We measure the flow with a known accuracy device, which we call a calibrator. Typically, we don't just stop with measuring the flow, we will adjust it to a known desired value for various reasons, some of which are operability of our equipment, some are simply our convenience. We do this because we have to know how much air has been drawn through our sample media. If we don't know that, we cannot calculate airborne concentrations for comparison to exposure limits. Sometimes we're dealing without exposure limits, comparison to what we know about toxicological data. Some cases, equipment is specifically designed to operate at a particular flow rate. Cyclone separators for particularly silica come to mind. Also for bioaerosol samples, we have to have a specific flow rate. Anything that depends on impaction requires a very specific flow rate. Bottom line, it ensures the accuracy and validity of our results. Started out back when I was young, we had dinosaurs. We used soap bubble meters. They work reasonably well. Run a soap bubble up a burette of a known volume, at least we hoped it was known. I checked some of the early commercial ones and they were off by sometimes as much as 7, 8, 10%. We would time it with a hand-operated stopwatch. It was simple, it was cost-effective, it was probably the best available at the time from a field perspective, but we had accuracy limitations based on some of the commercially available burettes. Soap bubbles would break off, form little bubbles on the side that would reduce our volume, give us false high readings. Repeatability was limited by our ability to hit the stopwatch properly, time and at the beginning and the end. So there were a lot of variability, but it was the best that was available at the time. There was no automation initially. Later, they did come up with essentially automated soap bubble meters. Rotometers came in. It's basically a variable area tube, tapered tube. Air comes in or gas comes in at the bottom. It pushes a ball or a float up to some sort of a calibrated mark. You see it a lot in laboratories and industrial settings right now, just as a visual flow indicator. The accuracy was not real good. It depended on fluid properties. You had to have frequent calibration. Just the tiniest bit of buildup along the walls of the tube would cause false high readings. We try not to use them currently, particularly the ones that look like they came in the prize in a box of Cracker Jack. Later on, we went to what they call a bell prover, which is basically an upside down can full of water floating in another pan of water. We would introduce the air or gas at the bottom, and that would cause the can to float up. Can was marked, and we would time the increase. It was analogous to the soap bubble meter. In very large scale applications, you can get some very highly accurate measurements, but it's not very practical out in the field. There were other devices, nightmares, such as the wet test meter, all kinds of things that wild and wonderful people came up with that didn't work very well and were not very field portable. Piston provers came in, basically more precise, more portable, as you can see on the extreme right side. Perhaps not as portable and field friendly as we'd like, but basically they measured the flow of or movement of a piston up a cylinder, timed automatically. We try and use primary standards to the greatest degree possible. They're traceable, they're defensible. A primary standard is a device or an object that is used as a reference that is derived from physical standards, measurable, time, distance, pressure, temperature, fundamental measurements that are traceable to national and international standards. As I said, physically measurable parameters, typically volume or the dimensions defining it, and time. Piston prover is basically a piston going up a cylinder. So it's the volume of the piston, volume of the cylinder, excuse me, divided by the time to give us a flow rate. It's fixed, it's linear, it's unaffected by the flow rate within any reasonable limits. We can standardize that flow by compensating for temperature and also absolute pressure, both of which are also measurable, traceable parameters. As we said, traceable to international and national standards. A secondary standard is based on analogy. We will look at, say, the change in resistance of a hot wire when we cool it by airflow, the change of the thickness of an aneroid, that's a sealed metal canister that generally it's pleated so it looks like an accordion. It expands and contracts with changes in exterior pressure and temperature, and we measure that either mechanically or electronically with a pickoff. Or the change in angle of a vein that's protruding into an airflow. They're indirect, they're nonlinear, they make a lot of assumptions that all of the hot wires and all of the veins and all of the aneroids behave the same. Sometimes you'll get a direct reading, sometimes it's massaged through an algorithm, but that algorithm, again, is its best approximation. So it's a little bit of a guesswork with a lot of opportunities to go wrong. The piston prover is a little more accurate depending on how well it's put together. The design concept is very simple. It's a volume displacement based on the length and diameter of the cylinder and the time that it takes the piston to go up it. It's frictionless, so we don't get drag from the piston going up the cylinder. Very high precision. As you can see on the right side, you've got a valve at the bottom. In its normally open position, the air or gas just flows right through. The valve closes, it introduces your air or gas under the piston. Piston goes up, it trips a lower detector, which starts a timer, upper detector, which stops the timer, and then also trips the valve back open to allow the piston to fall back. Simple in concept. The gentleman who came up with the dry cal principle was a gentleman named Harvey Padden, knew Mr. Padden, and as he told me, it was real easy to think of. It was very, very difficult in practice to get the piston, the cylinder, all the valves, the timers, the detectors set up correctly, and it remained difficult and very painstaking and requiring a great deal of skill in the assembly process. These are just quick and dirty. These are the pyramids of traceability and unbroken string of traceability for a primary standard. A secondary standard, you've got breaks for analogies and for having to calibrate a secondary standard with a primary standard. We're not going to put a lot of time into this. When you get the slides, you can take a look at it yourself. But basically, the secondary measurement has at least one level and sometimes multiple levels of analogy. I won't go so far as to call it guesswork, but assumptions at least. Our applications, as industrial hygienists, of course, we do a lot of industrial hygiene sampling. We also get involved in environmental sampling. Over the course of my career, I've done a fair amount of calibration and verification of process instrumentation. And then I've gotten into some very strange specialty applications that don't fall neatly into any particular category. For industrial hygiene sampling, our primary purpose is to determine employee worker exposures. We do a little bit of area sampling, both professionally and under some of the regulations, but not very much. Our contaminants are normally either gases or vapors for their inherent toxicity. Particulate masses, particulate limits are typically mass or count in the case of asbestos per unit volume. For industrial hygiene purposes, these are normally sampled at a medium flow, somewhere in the 0.5 to 3 or 4 liter per minute range. Since analytically these are measured directly, the temperature and the pressure don't really matter. We have sampled a fixed volume of air. The laboratory reports a fixed either mass or count of contaminant, and it's a simple process to calculate what our exposures are. Gas and vapor limits, a little more complicated. They're part per million or part per billion by volume. We typically sample at low flow. The laboratory analyzes, again, in mass. The limits are per standard volume, as we'll talk about just a couple of minutes. But our temperature and pressure have to be compensated for because we are talking about standard rather than physical volumetric volume. Regulatory and professional practice, we standardize for temperature and pressure for gas and vapor only. If we fail to do so, we've invalidated our sample. Also, if we have standardized for particulates, we have invalidated those samples. For some reason, the military tends to standardize for particulate samples. I have no idea why. I have never gotten a coherent explanation, despite the fact that at one time in my career, I had pretty much a daily relationship with a gentleman who had retired as the chief bioenvironmental engineer for the Air Force. That's what they called industrial hygienists. The reason we standardize for gases and vapors is because the body responds to the mass of contaminant that's inhaled or ingested, not to its concentration. Because they're gases and vapors, vapor is just the gaseous form of a liquid, they're subject to Charles' law, directly proportional to the absolute temperature, and Boyle's law, they're inversely proportional to the absolute pressure. So as pressure and temperature change, the volume of a fixed mass of contaminant either increases or decreases, either directly or inversely, depending on whether we're talking about temperature or pressure. We have our combined gas law that operates so that we can easily calculate what our standard volumes are. Normally in industrial hygiene, we standardize to 25 degrees C and 760 millimeters of mercury. Typically, environmental sampling is 20 degrees C and 760 millimeters of mercury. Occasionally you'll see something at 0 degrees C and 760. That's a very, very rare situation. You may think that standardizing or not is fairly trivial because we're operating, we think, room temperature, but it's not trivial at all. If you've got a 15 degree centigrade temperature change, about 27 degrees Fahrenheit, that's a 5% change. 1,400 foot altitude change is also about 5%. Give you an example. You have a hot day in Denver. You can have a 20% change just for the altitude of Denver. And on a hot day, you can have another 5% for the elevated temperature. So you can have a 25% change between your standard and your volumetric readings, which gives you a pretty substantial difference, easily able to push you into an area where you had concern or did not have concern as a false positive or a false negative. I do think that it's important to recall that standardization must be based on the temperature and the pressure of the area where we're going to sample. I was in a mine operation, an industrial hygienist or technician there, was taking samples. That's fine, but they were doing it in an office at the head of the mine, a nice air-conditioned office. It was nice and cool. They then put the samples, took them down to the mine that was several thousand feet deep, and it was deep enough that it was starting to get geothermal heating, and the temperature was way up. So you had, in this case, offsetting elevated temperature and increasing pressure. But sometimes, as we said with the Denver analogy, they can add rather than offset. So you can get all kinds of strange variations that have to be compensated for. We do have professional and regulatory guidance on this, so we're not just making things up as we go along. Of course, we do want our work to be accurate. It's both a matter of professional pride and a matter of professional necessity. Our standard practice is plus or minus 5% from pre-sampling to post-sampling calibration. We also have regulatory requirements. The OSHA and NIOSH methods are based on 5%. The EPA, a lot of them use the plus or minus 5%. Some are as low as 1%. Then asbestos is plus 0 minus 5%. The thought process is that they want to make sure that all the error is to the high side in the results. OSHA and NIOSH have guidance. Their general guidance for both of them are that we have plus or minus 1% with a recommendation for the use of primary standards as opposed to secondary standards. Obviously the NIOSH is purely advisory, but OSHA and a lot of their substance specific standards go beyond just a recommendation to a primary standard to mandate the use of a primary standard. And they use primary standards in their own work because it gives them defensibility. And environmental sampling is a little bit different, conceptually very similar in terms of the sampling media. The equipment is a little bit different, typically a higher flow rate, which means it's larger equipment that's not personal compatible, line powered in many cases, but typically higher than industrial hygiene sampling. Some of their particulate methods require standardization, some don't. You'll have to look at the method itself to determine which it is. The calibrator that we use depends on the method of interest, because the typical low and medium flow industrial hygiene calibrators may not work. You may have to use a high flow device. In all cases, you cannot use a piston type calibrator in a condensing atmosphere, because you get moisture inside the cylinder and the piston sticks, and generally that will not clear. It's tripped back to the manufacturer for disassembly, clean out, and reassembly. This is particularly the case when you're doing, say, stack sampling, where you got an awful lot of moisture at high temperature. Sometimes we'll have to do things like put in ice baths to cool that gas flow and condense the moisture out so that we can adequately calibrate and sample. And this is one of the situations where you're actually sampling for particulates in a volumetric, in a standardized rather than volumetric method. Sometimes we'll get involved in calibration and verification of process gas flow instruments. This is typically either a rotometer or a mass flow meter. For process control, you sometimes have extremely high precision, high accuracy devices that are beyond the capabilities of our typical industrial hygiene and environmental equipment. So if you get an instruction or commission to do this, you need to make sure that your calibrators are suitable for the task at hand. Again, can't use this in applications with condensing gases. Sometimes it'll be corrosive and flammable gases. These are concerns that have to be addressed case by case. I get inquiries fairly regularly, had one last week where they were looking at using hydrogen fluoride. They were unable to tell me whether it was wet HF or dry HF, but my advice to them was they have to accept the fact that with these corrosive gases, that they may have to accept a short calibrator life and equipment life, but it has to be addressed and assessed individually. Specialty, sometimes we'll see inline installations on particularly laboratory equipment. Mostly this is rough flow indication rather than extremely precise measurements. Tank and vessel headspace sampling, corrosive, radioactive, flammable applications. Did some work at the Hanford Nuclear Reservation where we had hydrogen, acid gases, and radionuclides all at the same time. That was another one where we were actually buying calibrators in batches of dozens. The atmosphere was just eating them up. They had very short lives, had to do an awful lot of individual determination. What was safe, what was not safe, what was within the calibrator's capabilities, and what was the calibrator's survivability. There are certain common pitfalls that can lead to invalidations of our samples. First, false results are expensive. If you got false high results, you have to put in controls that are unnecessary. You've got the installation cost, you've got the operational cost, any impacts on the production or the operation that they're associated with. Even worse, low results can jeopardize employee health and the environment. We really, really want to avoid that. particularly from a very parochial perspective as industrial hygienists, the employee health issue. Consideration is regulatory violations. Generally, if you avoided jeopardizing health, you're not going to have regulatory problems, so those are secondary. If you're dealing with process instrumentation, false readings will result in poor operation of the process, sometimes either shutdowns or catastrophic failures. And any false results are going to look bad. They reflect badly on the party that generates it. I mentioned that I do mostly expert witness work at this stage in my career. I love the field work. I'm in my mid-70s. I don't crawl and climb like I used to. But the expert witness work is a lot like Mortal Kombat without the blood. You say, well, that's pretty far removed from what you do on a day-to-day basis, but it isn't really. Generally, when we get into these sorts of things, it's because somebody erred or they were perceived to have erred, and they were the person that whoever felt injured is looking to blame. So we want to make sure that you don't end up being that person on the receiving end of the blame. Good practices. This is part of avoiding blame. Use the appropriate calibrator. Again, I tend to go with primary calibrators. I haven't used a secondary calibrator in I can't remember when, because it gives me a level of protection in terms of legal defensibility. Stay within the flow range of the calibrator. It's not too much of a problem with over ranges. Most of the electronic calibrators will simply shut down and quit reading if you go to an over range. If you go to an under range situation, it's slow. You may have accuracy suffer because the cylinder and piston on a primary piston standard are very, very precise fit, but there is a finite amount of leakage, and that leakage can cause a little bit of fall off of accuracy if you're below the flow range. Some calibrators will acknowledge that leakage, that they will give you an accuracy in a certain percentage or a fixed amount, whichever is greater, to reflect that type of leakage. For instance, we've got one that I'm aware of, I think says 1% or 2 cc's per minute. That's fine at 2 liters a minute, where it's 0.1% change. You slow it down to 20 cc's a minute, that's a 10% change, which is way outside of our tolerance. So you do need to confirm that your calibrator doesn't lose that accuracy down in that fixed flow error range. Primary standards, particularly piston provers, tend to be very linear, plus or minus whatever that 1%, or in some cases even less than that, across their full range. Some calibrators, if they give a range and you start to see that fixed amount of leakage or loss of accuracy in terms of volumetric cc's per minute, that can exceed that 1% accuracy. The reason that we look at 1% accuracy on calibrators is because we're looking at a 5% total, and we've got about 3% that OSHA says, but I think it was actually a NIOSH study, says is attributable to pumps. So they really want the calibrator accuracy not to be the limiting factor. They want the pumps, which tend to be somewhat less stable than calibrators, to be your limiting factor. Good practices, again, continued. Stay within your range. Stay within the requirements of your sampling method for accuracy and precision. Again, particulates for industrial hygiene are normally volumetric samples. at medium flow, gases and vapors normally, low flow and standardized. Always make sure that you have checked the method if you have the least doubt. For particulate sampling, you can use a volumetric sampler and you're good to go. If you're doing gas and vapor sampling, you can use a volumetric with a separate source to give you temperature and pressure. That's pretty awkward. There are pumps, calibrators that are available that give you either readings of your absolute pressure and absolute temperature, or that will actually do the standardization calculation for you. If I was doing very occasional gas and vapor sampling, I might go with a volumetric to save a few dollars. If I was doing a lot of it, I would go with one that did the calculation, both to save the calculation time and to eliminate the human error of dividing where you're supposed to multiply or vice versa. Something that we see, and I differ a little bit with the calibrator manufacturers, I and the professional guidance say calibrate with the sampling train in line. Some of the manufacturers say keep the shortest possible length of tubing so that you have better consistency, but always sample with the sampling train in line so that you're calibrating with exactly the setup that you're going to be sampling with. Document your calibrations. When I was with OSHA, we were told to calibrate and log it in a separate calibration log. What OSHA found out was that that didn't work out because industrial hygienists came, industrial hygienists went, transferred to different offices and took their calibration logs with them. They were bound documents. They didn't end up in the file, so they had defensibility issues. Normally, I'll put it on the sample data sheets, but you need to have the time, the date, the location, the device that you calibrated, the device that you calibrated with, what your calibrated flow was. For samples that require standardization, you need to log your temperature and pressure, and it needs to identify who actually did the calibration. Errors that we see, big one, taking a calibrator, particularly out of cold into a warm atmosphere. Everybody's gone out, come in from outside in the wintertime, and you've had your glasses fog up. Well, the same thing will happen inside your calibrator, except when that happens and you use a piston prover, the piston will pick up that moisture and there's a good chance it will stick. And as I said, it will not normally clear. It's tripped back to the factory. Even if you have not gotten into condensation, you've got different temperatures. You're pulling, say, a warm air into a cold calibrator. That air mass shrinks somewhat from the cold calibrator. The opposite with going from warm to cold and cold to warm, and you get different volumetric and standardized readings than is reality. Connecting the pump to the suction or to the pressure fitting instead of the suction fitting, it just simply doesn't work. You got to have a good charge on a battery because that valve at the bottom requires quite a bit of current to operate it. And again, standardizing or not standardizing when you're supposed to do the opposite. Problems, verify your battery is working. Most calibrators have a reset. Hit that. If that doesn't clear it, follow a troubleshooting guide. And worst case, go to the OEM for some tech support. What I see a lot now is the use of pumps from third parties. either rental or laboratories. Don't have a problem with this. Save the money if somebody is going to lend you pumps. If you're going to do something just once or twice, renting is probably cheaper than buying, but they've got to be calibrated, just like a pump you own. You need to know who calibrated it, with what standard, documentation. You need to be able to get that documentation. After it's done at a remote location, it's shipped to you. Rough handling, vehicles, airplanes, all of this can shift the calibration, even if it doesn't shift it when it gets to you. Sending it back can shift it on the way back. So you're not really sure what happened. If you're going to use your samples more than one day, requirement to sample and calibrate before and after each sampling. How are you going to do that with someone else calibrating your pumps at a remote location if you're doing multiple days of sampling? If they calibrated, was it the same conditions? Did they use the same sampling train? Did they use any sampling train at all? If you've done something like that, you get the calibrator or the pumps back to the laboratory or the rental facility. They do a calibration. You get a failure. You're going to have to resample, but you don't have the pumps anymore. If the samples came to the laboratory directly, particularly if you have rented the pumps, they may have been analyzed. You go back to the rental place and say it didn't calibrate properly. Now I'm on the hook for lab fees. They're probably going to say talk to the lab. If the lab did it, you may have a hateful discussion, but they may give you some consideration on the lab fees, but nonetheless, they're gone. If you had an operation that was very episodic, you may have simply lost your opportunity. It may take a long time to reschedule. So I do recommend, if you're getting pumps from outside parties, that you have your own calibrator. Save the money, and not buying the pumps is fine, but I do think you should have your own calibrator. A couple of quick case studies. First was an insecticide poisoning. Homeowner noticed termites in their kitchen cabinetry. They called an exterminator. Exterminator came in, applied termiticide that was prohibited from use after construction into a 30-year-old building. They didn't drill the injection hole all the way through to the soil. It was on a slab, so when they injected, they kept pumping it in, waiting for it to come out the relief hole, and it never did. It did buckle up the floor in second room adjacent, went house wide, came up through spiderweb cracks in the slab, went into the carpet. 2 dogs died. The husband was vegetated. The younger son was institutionalized. The older son and the wife were ill, but they recovered. For whatever reason, the exterminator's insurance company decided to really fight the issue. They sent an industrial hygienist out. He sampled fastidious documentation. Unfortunately, the documentation caused him all kinds of problems. His calibrations failed on post-sampling, and he did not standardize the gas and vapor samples. On top of that, the laboratory analyzed by an improper method. Again, this was all documented. So we came out looking very well in terms of problems on the other side, but did not go well in court originally. Took 2 trips up to the state Supreme Court. The judges had trouble with the concept of improper analytical method, particularly the use of an electron capture detector instead of thermal conductivity. They didn't understand that, but they could easily grasp the idea of failed calibration, and they kicked it back down to the lower court, and we were able to negotiate a very nice settlement on that because of calibration failures. Second case study was a little more complicated. Company was producing alumina, which is the first step in going from aluminum ore called bauxite to metallic aluminum. For whatever reason, they are not the agency with jurisdiction over that. OSHA is not the agency with jurisdiction over that operation. The agency that had jurisdiction didn't have a lot of technical capabilities. When I was overseas in West Africa and again in South America, we had found some mercury in some of the process equipment. I reported it to my client. They reported it to the EPA. It got back to the regulatory agency that did have jurisdiction. They sent an inspector out with a device that could not be calibrated, and they took a sample in the headspace of the first stage mix tank, which was operating at about 270 degrees Fahrenheit, maybe 130, 135 degrees centigrade, and full of hot caustic mist, not an occupied area. It essentially destroyed the instrument, but it failed in full-scale deflection. So they cited my client for a horrible mercury concentration. For whatever reason, they had a policy or procedure or regulation that you could not challenge their violation until you had actually rectified the problem and paid the fine. That was an impossibility. The only rectification of the problem that they perceived, which wasn't a problem, would be to shut the process down, which would have shut the entire U.S. Aluminum industry down. It actually went up to the Supreme Court. The Supreme Court, U.S. Supreme Court, decided it on due process constitutional grounds, but what got our foot in the door was that the device was not calibrated and was not capable of being calibrated. So calibration really is important. It's not the only factor in the integrity of our data and the validity of our data, but it is the first step. If we don't have validity at the first step, nothing else that follows matters. If you're in doubt, check your method and follow it. Keep your calibrators within their use limits. Document everything unless you're the poor guy in that first case study who fastidiously documented his own failures. And here I will turn it over to Ram for a few remarks, and then we've got a couple of minutes for question and answer.
Great. Thank you, Lawrence, for sharing those insightful case studies. Now that we have covered as to what may lead to invalidating of samples, let's look at why equipment maintenance is a crucial part and the role that OEMs play in this process. When you send your equipment or instruments back to OEMs for service, the objective is straightforward: restore it back to its original performance. OEMs built the product, so trusted source had built the unit. So this goes beyond just basic flow checks. OEMs will ensure that devices are cleaned, tested, recalibrated as a complete system. Sensors are verified, components are replaced, and any required adjustments are made to bring the unit back to published specifications. For primary flow calibrators such as, Lawrence, I think you may want to move back one slide. Sorry. Yeah, for primary flow calibrators such as defenders and dry cals, this includes verifying the very core of what goes into measurements. The glass and piston and the LED detectors that ensure gas volume and time of flight integrity are extremely crucial as part of the maintenance and recalibration process. So the take-home message here is simple: trust the source that built your unit. Next slide, please. So now that we've established why working with OEMs is critical, the next question is how do you ensure that the calibration itself is credible and defensible? This is where ISO 17025 accreditation becomes important. An accredited lab will have demonstrated through independent audit that it operates under a validated quality system. This includes controlled procedures, trained personnel, documentation of measurement uncertainty, and full traceability to national standards. For IH and OEHS applications, this directly impacts confidence in flow data, sample volume, and ultimately exposure results. These are only as reliable as the calibrations behind them. So once again, the take-home message is work with OEMs and OEMs who are accredited to doing the service. With that, that concludes our presentation on sampling integrity. So we would love to open up for Q&A. And also we welcome everyone to join and follow Mesa Labs on LinkedIn and other channels.
Okay, great. Thanks, Ram and Lawrence. Looks like we have about 7 or 8 minutes left for questions. Just a reminder, if you'd like to ask a question, please send it through the chat window. The first question I have is, when evaluating flow calibrators, which performance characteristics matter the most for ensuring defensible and audit-ready measurements?
Great, I'll take that one. In terms of sizing up which flow calibrator, I think there's a couple of things to keep in mind. One is accuracy over the flow range. It's extremely important, as Lawrence walked through in some of the examples, in ensuring that the stated uncertainties and accuracies are held over the flow range, especially at low flow, where gas flow and vapor sampling calibrations are extremely important. So, and that is critical in ensuring that it's being met with OSHA's requirements of plus minus 5% within post and pre and post calibrations. The other one is reliability, of course, and the ability to standardize calibrations, especially for gas and vapor, once again, where temperature and pressure have a significant influence based on geography. So you want to be close to the work site where you are doing the calibrations. So, you're compensating and factoring for temperature and pressure effects.
If I can jump in for just a second, we go to sample and we maybe have to take 8 samples. We'll bring 10 pumps. If we have a failure in a pump, we just put another one in, but we generally only bring one calibrator. So to me, it's very difficult to overstate the importance of the reliability of the calibrator.
Great, thank you. Next question I have is, one of our participants says that calibrating and sampling below 0 degrees Celsius can be challenging. Do you have any recommendations for working in environments below freezing?
Depends on how far below 0 Celsius. If you're a reasonable amount below, and I've sampled as low as about 30 below Celsius, pump and calibrator function is all right. Below that, your batteries may start to drop off pretty badly, but the standardization equations still apply if you're doing gas and vapor sampling. Volumetric is still volumetric. So as long as you are not so cold that you're starting to have equipment failures, I've never encountered a problem. It is unpleasant. I'll concede that.
Good point. Thank you. The next question is a two-parter. So Chris asks, does ASTM D5337 standard practice for setting and verifying the flow rate of personal sampling pumps do away with the terms primary and secondary calibrator slash flow meter? And does it also preferentially use the term verify over the term calibrate when using field user flow meters?
Okay, there's two answers or two ways, I guess, of answering that. First is ASTM doesn't really bind us, whereas we do have regulation that does bind. And so regardless of what ASTM says, we have to abide by the OSHA, the EPA, perhaps any other regulatory agency requirements. Even if it's not a requirement, you do have defensibility if you follow their guidelines. Second, I don't say that a secondary standard is absolutely unacceptable. If it meets the regulatory requirements, that's fine, but I would go back to a lot of the OSHA substance-specific regulations that do mandate a primary standard.
Thank you. The next question I have is, does Mesa Lab flow meter automatically correct the flow rate to standardized temp and pressure?
It depends upon the model. And Ron probably knows the fine distinctions better than I do. Some are pure volumetric, some display temperature and pressure, and some will actually calculate a standardized flow. Ron, do you have anything to add to that?
Yeah, so the Defender 530 Plus series calculates that for you, so it removes any potential for error. As Lawrence mentioned, there are two other models, the 510s, which does just the volumetric. The 520 captures both temperature and pressure. But we always recommend to having the 530 pluses that does the calculations for you. Also noticed through the chat, there are a lot of questions about the products, which we didn't get into in this setting. So we will certainly take those questions up and follow up with a lot of the questions that have come our way as a follow-up, and possibly have a second part of this that is more catered towards the product specifics and some of the questions that have come up for use cases and applicability.
Great, thank you. I'll try to pick one out here that's not product related to hopefully close us out. I have another question about if air transport affects the calibration, but some equipment is required to be sent to facilities, how do you control these possible variations?
That's why I suggest that you can save the money and use either rental or loaner pumps, but that you have your own calibrator so that the air transport takes place before you do your initial calibration and after you've done your post-sampling calibration, so that it is not a factor in your calibration or your chain of documentation related to it.
Great. Might be able to squeeze in one more if we could get possibly a quick answer. This person asks, if you're using a representative media, how often do you change that media out?
I will change if we're talking about calibration with the same sampling chain, I will make sure that I'm using the same batch of media, and I will use it for one sampling event. If I'm doing 2 or 3 days, I might use the same media because it's exposed for many hours in sampling and only a few minutes in calibration. But I don't just use it forever.
Great, thank you. Unfortunately, that's all the time we have for today. As mentioned, we'll be sharing all of the questions from today's event with Mesa Labs. So if we didn't get to your question, please know that we will pass it along. My thanks to Ram Parameshwar and Lauren Stereo for their presentation, to Mesa Labs for sponsoring today's webinar, and to all of our participants. Please check aiha.webvent.tv for announcements of upcoming Synergist webinars and to view recordings of our previous ones. Hope everyone has a great day.
Thank you, everyone.
Thank you.